So as I have discussed in the last video that I am going to elaborate one problem on this Dunkerleys method, and here is that problem. Let me read it out first. That a hollow shaft of 1.8 meter long is supported in flexible bearings at the ends. It carries two wheels each of 60 kg mass. First of all, you note down that 1.8 meter long and supported on flexible bearings. That means what? That it is the ends are not fixed, because depending on the flexible means you can consider them simply supported also. So if they are fixed, so some equations will have different will be different, but if they are flexible then equations will be different. I shall discuss them in due time. Now it carries two wheels each of 60 kg mass, so it is supported it is supporting two wheels. One is of 60 kg mass, both of them, one at the center of the shaft. So one of them are acting at the center. So due to that, the deflection will be W L cube by 48 EI. Okay, that deflection that we know due to a central weight, that is the deflection, expression of deflection for the case of a simply supported one. Now another one is at the center of the shaft, and other one is 450 mm from the center. So in either side another one is 450 mm. So it is 1.8 meter. At the middle it is 0.9 meter from one end. So from there, in one side it is 450 mm. So from the other side it will be 450 mm, and from another side it will be 1.35 mm, 0.9 plus 0.45. So for that also we know the formula, that is that W A square B square by 3EIL. Okay, so that is the formula for offset loading. I have discussed that in last video also. Anyway, the external and internal diameters of the shaft are 80 mm and 50 mm respectively. So the external and internal, that's a hollow shaft here. Determine the wheeling speed of the shaft, that is the wheeling speed either in terms of frequency, not frequency, wheeling speed. So you have to convert that frequency into speed. Density of the material is 7500 kg per meter cube. So from the diameters and the lengths, external and internal diameters and the length, you need to find out the volume and multiply it with the densities, and you will get the weight. That weight is not concentrated one, that is distributed over the length. So for that also you need to, if there is a uniformly distributed length weight, then 5 by 384 WL cube by EI, small w L cube by L to the power 4 by EI, that is the formula. Okay, and modulus of rigidity G, because the frequency is needed for that, G is given 210 giganewton. Giga means 10 to the power 9 Newton per meter square. So coming to the solution of the problem, you see flexible bearings, mass of depletion will be calculated by WL cube by 48 EI, and MI of the hollow shaft, mass moment of inertia will be cross-sectional inertia will be W pi d to the power 4 by 64. Okay, and as it is hollow, d1 to the power 4 minus d2 to the power 4. Okay, now you see it's not a torsional one, this is the transverse vibration, that's why d1 to the power 4 64 is taken. In case of torsional vibration, it will twist about the centroidal axis. In that case, the polar moment of inertia need to be taken, so that will be pi d to the power 4 by 32. So you need to understand this is the case of transverse vibration, and in case of twisting, that is the polar moment of inertia need to be considered. Due to transverse loading, the shaft is subjected to vibrate in the transverse direction. Hence, MI is considered pi d to the power 4 by 64. In case of torsion, pi d to the power 4 by 32. That's what I have just said. So I can be calculated with 1.7038 into 10 to the power minus 6 meter to the power 4. I have not shown you the detailed calculation here. Now you see here, that's the figure. You see it's on flexible bearings. Centroidal load is 60 kg, which is here, and there is a offset loading which is here. Okay, this one, that is also 60 kg. Okay, so it is 0.9 meter from the midpoint and 0.45 meter from this side. So as it is 1.8 meter, so from one end it is 1.35 meter, and another one it is 0.45 meter. Okay, mass, now I am calculating the mass, area into density. So that is diameters are given pi d square by 4. So as it is hollow, so I need to subtract into the density and per meter, mass of the shaft per meter, because that is the value I need while calculating the centroidal deflection due to uniformly distributed load, I need the mass per meter. Okay, so that's why this 1 is multiplied, and here is the density. So 22.973 kg per meter. So at the end, I shall use the Dunkerleys method, but before that, I need to know the deflection due to each of this node. So there are three types of nodes here. One is the centroidal node. For that, this is the deflection expression. For that is the static deflection due to the 60 kg at center. Now, second one is static deflection due to the load which is not at center, W A square B square by 3EIL. So for the first case, I found that using the formula is given, everything is given here apart from this W1 is 60. So I need to convert it into weight by multiplying into 9.81. L is 1.8 meter, already we know. 48, E is 210 giganewtons so per meter square. So I calculated that one, and I just now I have calculated from this one. Okay, so I got this 1.9987 into 10 to the minus 4. Now that is the deflection, and deflection due to the offset loading is W2 A square B square 3EI by L. So W2 is also 60 kg. So from there also, using the formula, I got that. You see there I have elaborated. Okay, A is 0.9 plus 0.45 1.35 meter, and B is 0.9 minus 0.45, which can be understood from this figure also. Okay. So using this formula, I got this expression, that is the delta 2 1.1243 into 10 to the minus 4 meter. That is the delta 2. Please, you have to understand that while finding out the frequency and the RPM, whatever you say, for that deflections due to these loads are important. So first you have to identify that's a fixed bearing or flexible bearing. Then depending on that, the deflection expression you need to consider. If it's a central load, then there will be one expression. If it's a uniformly distributed load, there will be another expression. If there is an offset loading apart from the center, then there will be another expression. Now delta T is the static deflection due to the uniformly loading throughout. So 5 by 384 WL to the power 4 by EI. So that W is weight per unit meter per meter, mass of the shaft per meter. Okay. W is mass of the shaft per meter, which is 22.973. Already we have calculated. So I have substituted that one here, and L to the power 4 is 1.8 to the power 4. EI is already given. We have calculated. So we got this 8.6074 into 10 to the minus 5 meter. So from the Dunkerleys formula, frequency of transverse vibration is 0.4985 delta 1 plus delta 2 plus delta S by 1.27 whole under root. So if you go on calculating this one, I am getting that 25.569 Hertz. So if I multiply it with the 60, so I am getting the RPM. That is what this question has asked, that determine the wheeling speed. That is the wheeling speed of the shaft. Okay. So if you have any doubt, because this sort of problems will have different loadings only on the shaft, you need to consider that what type of support it is having. You see in this case, when it is on flexible bearing, 5 by 384 WL to the power 4 by EI. But when it is fixed at both ends, means when there is a fixed one, then you due to central load, it will be WL cube by 192 EI. For the central load, in this case, it is simply supported or fixed. You can say that flexible bearings, then it is 48 EI. But in case of fixed one, that is WL cube by 192 EI. So depending on the ends, this will change. So in this case, if it would have been a fixed bearing, then this formula would have changed. Okay. So you need to find out that what type of bearings it's this one. You need to understand that what types of loadings are there. If it's a central loading, so you have to use this formula. If there is an offset loading, you have to use this formula, this one. And if there is a, for uniformly distributed load, or suppose the mass is given or the density is given, you need to understand that uniformly distributed load is there. In such case, you have to use this formula to find out the deflection. Once all the deflections due to loadings are obtained, you can use this Dunkerleys formula. You see, if the uniformly distributed loads are absent, in such case this delta S will not be there. Then you can find out that delta 1 plus delta 2 plus delta 3 whole root ऐसा कर सकते हो. Okay. So from there, once this frequency is obtained, we are getting the RPM. Okay. I hope this is clear and you can solve any of such problems. If you come across any typical problems on this topic, then definitely you can share. I shall help you to solve it. Thank you.